Okay, so first thing to do is to play around with this vector 3, 1. The first thing to do is to calculate the normalized value of this vector. And of course I was very wrong to do it in the very bad sequence. Okay? If you understand what normalization is, okay, you should know that in order to normalize something, you first have to calculate the magnitude, and find its magnitude is number 2. So I will now change the sequence and will first calculate the magnitude. Magnitude is, of course, a square root of both parts of this vector squared. 3 squared plus 1 squared, so it's square root of 9 plus 1, so it's square root of 10. So we have one thing done. Please remember that square of a negative number is always positive. Okay, in the short test a week ago, some people had something like this: minus 2 squared plus minus 2 squared, and you told me that this is a square root of minus 4, and it was square root of minus 8. Absolutely wrong, okay? Because minus 2 squared is 4 plus 4 should be square root of 4, not of 8, not minus 8. It's not for today. Today the result is square root of 10. Normalize the vector. Normalized vector. You don't have to be very strict with these symbols here. It's my vector 3, 1 divided by square root of 10. So this is vector 3 over square root of 10, 1 over square root of 10. That's the correct answer for this question. You can continue this calculation to make it looking better and multiply both numerator and denominator by square root of 10. And in this case we will get 3 roots of 10 over 10 and 1 root of 10 over 10. It looks a little bit nicer, but as I told you, if you leave it in this form, it's perfectly fine. Find its inverse vector. Inverse vector is simply minus v. It's minus 1 multiplied by this vector, okay? So it's minus 3 minus 1, probably the easiest possible question in vector algebra. The next question, has anyone got this right? 2 vectors that are parallel to v. Any answer? Yep. 6, 2. Yes, very good, very good. So if you are asked to find a vector which is parallel to any other vector, just multiply it by any number. So I will take, as you did, 2 and 3. So examples of parallel vectors are 6, 2, 9, 3. Okay. This is also technically a parallel vector. This is the inverse vector, so the vector pointing exactly in the opposite way, but still it is parallel to this because it's the v vector multiplied by minus 1. And if I'm moving, find 2 vectors that are perpendicular to v. Anyone got it? Perpendicular? That's a nice trick. I've been talking about it in the lecture, okay, but there might be a question like this in the test as well, so we have to go through this. We just swap both coordinates, so a perpendicular is, we had 3, 1, so we will swap them, so it's 1, 3, and additionally we need to change the sign of one of these. Okay, whatever, whichever of these. So a perpendicular vector might be -1, 3, or 1, -3. Okay, I could be even more creative here and say that also 6 - 2 will be perpendicular, longer, okay? Because this is parallel to this, it's just this vector times 2. So if something is parallel and this parallel vector is perpendicular to my vector, the other vector is also perpendicular. Okay? If I have a vector and a perpendicular vector here, each vector which would be parallel to this vector will be also this side, this way down. They would be all perpendicular. That's the end of question 1. We have now question 2. In question 2 we have a parametrical equation of a line which is pk equals p0 plus kv, where k is a parameter, so it's any number. If you put all the possible numbers, you will get a diagram of the line. Okay, but p0 and v are some values. So p0 is a point with coordinates -2. So let's imagine this is a point somewhere here, p0. Okay, and v is the same v as we had in question 1. Okay, so this is v in question 1. In question 2, we will use the same v. What it means, this v is free one, so this is a vector something like this. This is the vector v. Okay, and this parametrical equation of the line means that we can actually scale this v vector by providing k with any number from 0, 0.1, 0.2, up to 1, 2, 3, 4, up to plus infinity, and the other way around to minus infinity. So we can get any point which is on the line, which is defined by this point p0 and the vector v. Okay, we know the coordinates of the point p0, -2, -2, and we know the vector v. We actually know this vector very well because we've done already the question 1, which was all about the vector v. And the question now is find one normal vector for this line. Do you remember the definition of a normal vector? Yes?
It's the vector which, isn't it just that intersects at a 90-degree angle?
Yes, so we call it perpendicular. Yes.
And it's obviously normalised.
Normalised, yes. So it happens that we nearly have it done because we already have perpendicular vectors like this -1, 3, 1, -3, -2, 6. Okay, so these are perpendicular vectors already. The only thing that we need to normalize them. Okay, I will take this vector because this vector is very handy. I will call it n, my normal vector. I will just check if the camera is recording this. Yes, it is. So my vector n is one of my perpendicular vectors. I will take this -1, 3. And because the normal vector is not only perpendicular but also normalized, I have to do the same thing I did previously to find the normalized vector. I will divide it by the magnitude. What even nicer, I don't have to calculate the magnitude because I have chosen a vector which apparently has the same magnitude as v. Okay? If you just think about it, this is 3 squared plus 1 squared square root, okay? And here it's minus 1 squared, which is the same as 1 squared, plus 3 squared. It's the same length, okay? It's just instead of a vector like this, okay, it's a vector like this, okay? So this length will be square root of 10. Therefore, very quickly I can, looking here as a hint, I can tell you that one of these vectors is square root of 10 over 10, 3 square roots of 10 over 10, and I need a minus here. Okay, that's one of the normal vectors to this line. And double check if it's recording well. Yes, it is. And not surprisingly, this normal vector is strictly perpendicular to our normalized version of V. This and this are the same vector, but we swapped these coordinates and we've added minus in one of them. Who tell me, because it says a line has two normal vectors on a 2D plane, you just need to find one of these, okay? But anyway, what's the other one? The other normal vector. If I have a line like this vector that I have just calculated looks like this. This is my n. Okay? Who knows what is the other normal vector for this line? Yes, exactly. Yeah. It's just right here. Okay? Well, exactly two of them, one above, one below, no more, sorry, because the normal vector must be normalized, so anything longer or shorter than this cannot be. And coordinates of this other one will be exactly the same, but the minus sign will jump here. So it's inverse of the normal vector number 1. That's the end of the question number 2. Exercise number 3. Your velocity vector is minus 2, 4. What is your speed? This is one of the easiest questions in vector algebra. Okay. Many people didn't get it right in the test last week. The speed is nothing else but magnitude of the velocity vector. So this is square root of, so it's properly, minus 2 squared plus 4 squared. And unlike some people believe, square of minus 2 is 4, not minus 4, plus 16. So what we get here is square root of 20. Am I right with this? 16 plus 4, 20. Yeah. And again, if you leave it like this, it's perfectly fine. You can go a little bit further because 20 is 5 times 4. And we know what is square root of 4. Square root of 4 is 2 roots of 5. This is a slightly better answer, but you will not be losing any marks if you don't show it in this form. So feel free to stop at this moment. The question also asked about the normalized direction vector. So we are actually doing the same stuff as we did in the question number 1, just the terminology changes. Okay, if we are talking about velocity, then the magnitude of the velocity vector is called speed. If we are talking about velocity vector, then normalized velocity vector is called normalized direction. So if the question is about the normalized direction vector, this means nothing else but
again we have to
n minus 2, 4 divided by my 2 square roots of 5. So it's minus 2 over 2 square root of 5, 4 over 2 square roots of 5. I will go one more step because it's very nicely minus 1 over square root of 5 and 2 over square root of 5. And now optionally you can multiply both numerator and denominator by square root of 5 to get minus square root of 5 over 5 and 2 square roots of 5 over 5. Okay? That's the normalized direction vector. Question 4. My current position is 2 minus 3, and I am heading toward a point minus 6, 3. So this is my movement. Okay? I am at this position, 2 minus 3, and I am heading towards minus 6, 3. My speed is 2.5 units per second. Okay? So this shows this is a little bit different approach. Previously, and in the test last week, you had a velocity vector given, and there were questions arising from that. Now we know the current position, we know some position in the future, and we know the speed. And the question now is how we can find, because find the time you need to arrive to the destination point if your speed is constant. Okay? There's a little bit of physics in this question, because from physics we know that time is distance
over speed.
Yes. Okay. So my distance, this is very easy because it's nearly not a vector algebra question. My distance is a square root of something squared plus something squared. Who would tell me what I should put here? 2 minus 6. Yes? Okay, so it's the difference between this and this. And here,
2, 6.
minus 3, minus 3. Okay? That's good. That's perfectly good, particularly that even if I get negative numbers here, negative numbers, don't rewrite it because I will change it. Okay? It's formally, technically, and mathematically good. It's methodically not the best thing to do because, and I will insist you to do, I will not penalize in marks if you do the other way around, but normally if this is your starting point and this is your ending point, you should just create a habit in you. You always take the end of the motion minus the beginning. To calculate the distance, which is a number, a distance from London to Birmingham is the same as the distance from Birmingham to London. It doesn't matter. But in any other case, in vector algebra, it will most often make a big difference. So I take this minus 6 minus 2. Okay? And here 3 minus 3, it's plus 3 actually. Okay? So that's my calculation. It's mathematically the same thing, but a little bit better approach. So minus 6 minus 2, it's 8 squared. It's 64. And 3 plus 3, it's 6.
Nintendo 64.
So we have 64 plus 36, it's square root of 100, it's 10. So this is my distance. And now time I need is my distance, which is 10, divided by my speed, which is 2.5. This is 4. Actually, because the speed was in units per second, I even know that these are 4 seconds. So this is 4 seconds. Okay? A funny thing, because we don't need to calculate velocity vector, direction vector, we just calculated distance, we have speed. Okay, so it's nearly not a vector algebra question. Still, it's quite nice and quite easy to calculate. The next part, next question, is for the same situation, for the above situation, find your position 10 seconds after passing your destination point -6,3, if your velocity doesn't change. This time we have to find the velocity vector. Okay, we also have because we will be using the motion equation. Okay, we know our starting point. This is actually this point this time, because this question says after passing our destination point 10 seconds later. Okay, moving 2.5 units per second, 10 seconds later we will be 25 units away from this point, but we don't know yet exactly which direction. So we will need velocity vector. To get the velocity vector, we will need to find the direction vector. And for the direction vector, we have everything that we really need. Because we have this thing here. We can calculate something that is called displacement vector. And many of you have forgotten to calculate the displacement vector in the short test. Okay? Displacement vector is a very useful thing, and it's nothing else but the end of your journey, -6,3, minus the beginning of your journey, 2 minus 3. And this is very similar to this calculation here. So I have -6 minus 2, -6 minus 2, so it's -8. 3 minus -3, it's 6. Okay? So this is my displacement. Displacement is the direction, but it's not normalized. I'm standing here, I'm going there, so this is the vector telling you I'm going there. To have the normalized direction vector, which I usually call n, but it's my symbol, you have to take this vector and normalize it. -8.6 over, who would tell me what's the magnitude value for my velocity? Yeah? Sorry?
Yeah.
So, whoever thought that I should put 10 here was absolutely and perfectly right. Okay? Because that's the distance, that's the length of this vector. This is displacement. Okay? The length of the displacement is 10. It's been already calculated here. So my normalized direction vector is easy to find: -0.8, 0.6. Okay? Now, velocity vector, because this is the direction in which we are moving, so the velocity vector will be the same direction. So velocity vector will be basically the same vector as we have here as the direction, but multiplied, scaled by what? What is the magnitude of the velocity vector? Anyone? Magnitude of the velocity vector is speed. And our speed is 2.5, and this is the moment when I should put 2.5. 2.5 times 0.8, it's 1.6 minus 2. And the second part is 1.2, 1.5. This is my velocity vector, okay? So we started with the displacement vector, which was directly the end of my initial, my destination minus my starting point. My destination minus my starting point, this is the displacement. Then this displacement has been normalized to get the normalized direction, okay? Then I multiplied this by the velocity, okay? And I get something like this. You may notice that this and this are parallel, they are similar. This vector is 4 times longer. Because actually this vector shows you where I arrived after 4 seconds. You remember from the previous calculation here, the time of this journey was 4 seconds. So this is how I displace myself over 4 seconds. And the velocity tells you how you displace yourself over 1 second. And now position after 10 seconds, starting from this, after arrival to the destination point. So we start with minus 6,3 plus 10 times minus 2, 1.5. This is minus 6,3 plus minus 20, 15. So it's minus 26. If there is no, I think it's good. Minus 26. And the second number is 3 plus 15, it's 18. That's the result for question number 5. The next question says, thinking again about your initial position 2 minus 3, this one, your velocity is as calculated in the previous questions. So we have this velocity here, and there is a main question, are the points 0, 0 and 10 minus 2 ahead or behind you? And another pair of points, question is, are they on the same or different sides of my route? I need to wipe this whiteboard. So the whiteboard is now much more white. I've only left 2 minus 3 vector as the position, and minus 2, 1.5, which is the velocity calculated in the previous question. It was question number 5. At this point, I will draw a picture showing where we are and where are other points. So our current position is 1, 2, 1, 2, 3. It's 2 minus 3. It's somewhere about here. The velocity vector, current velocity vector, is 2 minus 2. So it's here, and 1.5 will be something like this. So that's the velocity vector. By the way, we shouldn't leave vectors just unnamed. So this is the velocity, and this is position, something like that. Okay, now when we have our position drawn, this means that this direction is a kind of our front, and this is back or rear. The question is, there are 2 points provided here. One point is 0, 0. So one of these points is right here, 0, 0. And another point is 10 minus 2. So this is 2, 4, 6, 8, 10 minus 2. It's somewhere here. Okay, so the question is this point ahead or behind, and is this point ahead or behind of our course? Okay. To solve this problem, first of all, we can see it. Okay, so we have some visual clue right now that 0, 0 is in front of our moving object. 10 minus 2 is behind the object. But of course, we have to calculate it. Computers are great in drawing pictures like that, but total rubbish in interpreting pictures like this. So we have to do this interpretation, and this interpretation may only be done in the calculational way. What we need are displacement vectors from our current position to one point and the other point. So now I can start with calculating these vectors. The first point was 0, 0. Therefore, its displacement d, let's call it d1. It's always the end of destination. So in this case, this is the point that we are testing. So it is 0, 0 minus the beginning of this arrow here. So it's our current position, 2 minus 3. 2 minus 3. This is 0 minus 2 is minus 2. 0 minus minus 3 is 3. Please don't do silly mistakes in the test. Don't tell me that 0 minus minus 3 is minus 3. Okay, it's 3. So these are coordinates of this vector here, this vector. And for the second point, it's the coordinates are where is this? 10 minus 2. Therefore, the second displacement is 10 minus 2 minus 2 minus 3. 10 minus 2 is 8. Minus 2 minus minus 3 is the same thing as minus 2 plus 3, so it's 1. Additional advantage from having pictures, images like this. First of all, you will not get any mark for reading the answer from this image. It has to be calculated. But once you have this image, you can visually control, you can visually check if your results are reasonably good. So minus 2, 3, it looks very much like a minus 2, 3 vector. Particularly if we know this is 3 is here, 2 is here. I know this because my coordinates were 2 minus 3. So this looks very much like minus 2, 3. And this is very likely to be 8, 1. No problem. Okay? So we have these displacement vectors right. To find whether something is ahead or behind of us, we have to take the velocity vector, the red one, which shows you the front of the moving object, and one of the displacement vectors. So, for object number 1, this will be my velocity. Velocity is minus to 1.5, and I will do quick and easy manual way of calculating dot products. I will just write the other vector, which is displacement minus 2, 3. Okay? A horizontal line, and now we will multiply this by this. Minus 2 times minus 2 is 4, without a minus. 1.5 times 3 is 4.5. This is our, let's call it, you don't actually have to do it, but I prefer to be correct, mathematically correct. So V dot d1 equals this. We have to add the two numbers together, and we have 8.5. This means front. Okay, front, I know this because the dot product of these two vectors is positive. Okay, if everything is correct, for the second operation, the dot product of my velocity is minus 2, 1.5, and the second displacement vector is 8, 1. So if everything went well, the result of velocity dot d2 should be negative, because from the picture I can see that the second point is behind me. So minus 2 times 8 is minus 16, and 1 times 1.5 it's 1.5. Added together is minus 14.5. The result is negative, therefore it's behind. That's just half of the question, because the second half tells are the points minus 2, 2 and minus 2, minus 2 on the same or on different sides of my course. The coordinates of the other 2 points. This is the point minus 2, 2, and the other point is minus 2, minus 2. And let's draw them here on this diagram. Minus 2, it's somewhere here. That's one point. And the other point is minus 2, it will be somewhere here. Okay, so point number 2. 1, point number 2. What it means whether these points are on the same or on different sides of my course. My course is, of course, the line, the straight line along which I am moving through this surface here. This course is defined by my velocity vector, so this course is here, and if everything is correct on this picture, you can clearly see that my points are on 2 different sides of this course. But of course they might be, as well, here and here would be both on the same side. Of course, any calculation done, any solution done by reading this diagram would be not enough in a in-class test and wouldn't be very applicable for the programmer, generally speaking, so that we have to do the proper calculations. In order to make these calculations, we will again consider displacement vectors which connect my current position 2, minus 3 with the point minus 2, 2, and then with minus 2, minus 2. So, let's calculate the first of these displacement. I will call it d3 because we've already had the displacement called d1 and d2 previously, so it's now d3 equals my target coordinates, so it's minus 2, 2, minus my initial position 2, minus 3, minus 2 is minus 4, 2 minus 3, it's 5. And looking at this picture, it's quite likely that this is 1, 2, 3, 4, and 5 to the up. This is probably minus 4, 5. Displacement number 4, it's these coordinates, minus 2, minus these coordinates, 2, minus 3. So what we get is minus 2, it's again minus 4, like it was here. Okay, but minus 2 minus 3 is it's 1. Okay, minus 2 minus 3, it's the same thing as minus 2 plus 3, so it is 1. And again, looking at the picture, minus 4, 1, it's quite likely it's true. To find out which side of the course, left or right it is, we have to again calculate a product, but this time it will be a cross product of velocity and each of these displacement vectors. So once again I will put the velocity here, minus 2, 1.5, minus 2, 1.5, maybe in a longer distance, minus 2, 1.5, and this is our case number 3, so I put D3 here, minus 4, 5, and here, minus 4, 1. But this time we'll be calculating cross product. So this is V cross D3 equals, and here V cross D4 equals something. Cross is multiplying things along a cross. So minus 2 times 5, minus 2 times 5 it's minus 10, minus 4 times 1.5 it's minus 6. Okay? And the cross product also, the formula for cross product has a minus here, not plus. So we have minus 10 minus minus 6, so it's minus 10 plus 6, but it's still a negative number, it's minus 4. Okay? And the same approach here, minus 2 times 1 is minus 2, minus 4 times 1.5, it's minus 6, minus 2 minus minus 6 is minus 2 plus 6, but this time this is a positive number and this is 4. We have two results. One is minus 4, the second is 4. This means that these are two different sides of the root. If we were very careful, we could actually quite easily find out which of these is left and which of these is right, but in this particular question, the question was simply about are these on the same side or two other sides. So if we have one negative, one positive number, this means that they are both on two different sides. Thank you. The next exercise is about two balls, one with the velocities. We don't know coordinates of these balls, but velocity of one ball is given as 2 minus 1, and velocity of the other one is 2, 2. We also have a wall with a normal vector. This normal vector is 0.1 square root of 10, 0.3 root of 10. So this normal vector is 0.1, 0.3, more or less something like this. Okay? Therefore, the wall looks like this. And in addition to that, we have two balls. Let's say they are somewhere near this wall. Velocity of one of them is 2 minus 1, so it's something like this. And the other is 2, 2, it's something like this. My picture is intentionally very, very bad quality, so I can't actually say if this ball is going to bounce from this wall or fly away. This definitely looks like flying away, but this one maybe just my bad scaling make it appear like flying away. So we have actually no other possibility but calculate the dot product of this velocity and this normal. I will add symbols on the picture. So this is my normal vector, and this is velocity of ball number 1, ball number 2. Okay? So in order to find out, we have to calculate dot product of V1 and N and dot product of V2 and N. V2 and N will probably, it looks like a positive value of the dot product because apparently these two vectors are pointing in the same direction, but we don't know about these two. Okay, so again, case number 1, case number 2, velocity 1 minus 1, here 2 and 2, and we have 0.1 square root of 10 and 0.3 square root of 10, and similarly here 0.1 square root of 10, 0.3 square root of 10. One calculation, the other calculation, this will be v1 dot n, this will be v2 dot n. Let's calculate it. 2 times 0.1 root of 10, it's 0.2 root of 10, plus minus 1, 0.3, it's minus 0.3 square root of 10. So I will draw a line here. Sorry, I counted this a little bit too much. 0.2 minus 0.3, it's minus 0.1 square root of 10. So we have the answer for the first one. It's a negative number. This was the calculation for this. This is a negative number. This means that velocity is pointing the other direction than the normal. So my drawing was wrong. In fact, but it was intentionally wrong. It's simply this velocity is nearly parallel to the wall, so it's probably more like this. Okay? From the image, from the diagram, it is very difficult to read in this case, but from the calculation, it leaves no doubt that this ball is going to bounce. Okay? How about the second one? I'm nearly sure that in this case the result will be positive, and it basically is, because it's 0.2 square root of 10 plus 0.6 square root of 10, so it's 0.8 square root of 10. Basically a positive dot product shows that the velocity of this ball is in the same direction as the normal of the wall, therefore we have no bounce in this case. And the last question in this paper, not counting the two ones that have stars, so they are marked as very difficult. For the marble hitting the wall, so that's this one, find its velocity after bouncing off the wall. We can use a reflection vector formula, which is ready for you to use. So it's this exercise is actually a no-brainer. This velocity after the bounce is given with the vector with the formula saying that this is the original, the initial velocity, minus 2 times v dot n times n. Now, to clearly understand which data we need, we have the velocity. It's the velocity of the first ball, because this is the ball that is bouncing from the wall. So that's the velocity. This is the normal. And we also have calculated v dot n, which is here. This is the dot product v dot n. So my velocity is 2 minus 1, then minus 2 times, this is my dot product, which has been calculated here. I hope it is correct. Yeah, it looks like correct. This is minus 0.1, so I will have plus here, okay, because minus is a plus. 0.1 square root of 10, and finally I have to multiply it by the normal vector, which is 0.1 square root of 10, 0.3 square root of 10. So this is equal, 2 minus 1 will be rewritten. 2 times 0.1, square root of 10 is simply 0.2 square root of 10. So that's this calculation. Now 0.2 times 0.1. 0.2 times 0.1 it's 0.02 times square root 10 multiplied it gives 10. And the second part is 0.2 times 0.3, it's 0.06 times, again, square root of 10 times square root of 10, so times 10. Okay, so we get 2 minus 1 plus 0, 2, 0, 6. So the answer is 2.2, and the second one is minus 1 plus 0.6, so it's minus 0.4. Non-mandatory part, this is the answer, the final answer for this question. So this is the velocity after the bounce. And this is the velocity before the bounce. Before it was 2 minus 1, after it's 2.2 minus 0.4. If you want to double check if our calculation is correct, we can do this following additional step, which is calculating the speed before the collision and after the collision. The bounce like this with ideal reflection should not, it changes velocity because it changes the direction, but it does not change the speed. So the speed 1 is square root of 2 squared, so it's 4, plus minus 1 squared, so it's 1, so it's square root of 5. The speed of velocity, not v1, it's v1 time velocity, speed after the bounce is the magnitude of this vector, so it's a square root of 2.2 squared plus 0.4. I can drop the minus because while squaring minus doesn't matter. 2.2 squared is 4.84. I have pre-calculated this value before. Okay, 0.4 squared is 0.16. You can clearly see that this ends up as square root of 5. So our both speeds are exactly the same. So probably we haven't made any mistake in these calculations.